This disrespect.
Okay, welcome to the first afternoon session. So I have the pleasure of introducing Lisa Ostrin from the University of Houston. She is one of the world's experts in myopia, and especially the animal experiments needed to develop ways to understand where myopia comes from. So she'll be giving a talk on the interaction of near work and light on the accommodative response in the choroids. That is also proven more and more to be a very important structure in myopia development. So please, Lisa.
Thanks, John. Can you see my slides okay?
Yes, we can.
Okay, great. So we're going to shift gears a bit from wavefront operations and talk about near work and light on the accommodative response and choroid in the context of myopia. And for my disclosures, I do some consulting and get some research support. But now going on to amortization in myopia. So when infants are born, there is a broad range of refractive errors that generally span and potential effects of new work on myopia risk. And for this particular talk, I'm going to be focusing on mirror work. And this is some of our most recent data coming out of the lab, our most recent experiments. So I'm excited to share them with you today. So first of all, why possibly would mirror work drive myopia? And there's two prevailing theories on why that could be, the optical theory and the biomechanical theory. So starting with the optical theory, the thought is that when children are accommodating, their accommodation is not accurate, leading to a lag of accommodation, which induces optical defocus, peripheral hyperopia, which is believed to be a signal for the eye to grow longer. So the eye has an emmetropization, tries to meet that focal plane. So this peripheral hyperopic signal is a cue for the eye to grow. The biomechanical theory states that with contraction of the ciliary muscle during accommodation, it puts stress on the posterior eye. So everything is kind of pulled forwards and centripetally inwards during accommodation. And those stressors on the choroid, on the retina, on the sclera, ultimately lead to tension on the posterior eye and scleral remodeling and axial elongation. So we're interested in these two theories and trying to parse out which one is contributing to the influence of mirror work on myopia. Thinking about structural changes, I want to introduce here the choroid. So as Scott said, the choroid is proving to be a really interesting structure in myopia. It is the vascular layer that supplies the outer retina and the sclera with oxygen and nutrients. And it's been shown in numerous studies that myopes tend to have a thinner choroid. So here we we measured axial length and choroidal thickness at baseline, 10 minutes, 20, and 30 minutes during that near work task. And the adults also returned in the evening to see if there was a time of day effect. So here you can see measuring axial length, and for choroidal thickness, we use the spectralis OCT and do a macular radial scan and use a 70 program to segment those layers and quantify choroidal thickness in the 1 millimeter central diameter of the retina. So first we'll look at the children's results, and as I mentioned, they read a printed book, which is shown in solid symbols, or watched an electronic movie shown in the open symbols. And indeed, we found that axial length increased forms of reading of mirror work. And choroidal thickness, while it did tend to decrease, it did not reach statistical significance. So what we found from this is that the axial length did increase, and it did not appear to be different whether they were reading on a book or on a backlit electronic device. And I should mention, for all of these studies, our participants are reading at a 20 centimeter distance, so a 5 diopter demand. Moving on to our adult results. These are freshly analyzed, and so I do not have statistics on these yet, but I wanted to include it here. So for axial length, we can see over time that it tended to elongate like it did in the children, and the choroid tended to thin here. Again, the black closed symbols are print reading. The open symbols are iPad reading, and the red is reading print in the evening. So what we see is that the patterns are similar for the different media and times of day, although it potentially reading in the evening has less thinning than reading the book in the morning. So we'll know for sure soon. And with that, I'll just move on to the next study, where we now add an extra layer of doing this reading in different types of lighting environments. So in that same room, earlier, we have the ability to illuminate the room with narrowband light. So for this experiment, we asked our participants to perform 30 minutes of newer and either broadband white light, narrowband blue light, narrowband red light, or we just asked them to watch a distant TV with no accommodation in broadband light. And so we measured again choroidal thickness and axial length at baseline, and then after the 30-minute task, and again after 30 minutes of recovery. And it was the same participants that came back 4 times, all 4 conditions in a randomized order, and at the same time of day. So moving on to those results, in the graph we can see change in axial length or change in choroidal thickness after the 30-minute near task and after 30 minutes of recovery. And for this experiment, this was young adults, we found that axial length increased and choroidal thickness decreased when doing the near task in broadband light and red light, but not when doing the task in blue light or the control condition of using a distant TV and broadband light. So something about reading in blue light seemed to mitigate the effect of this choroidal thinning that we saw in other conditions. And we saw that this returned to baseline for all conditions except broadband light. The axial length still seemed elongated after 30 minutes of recovery. So with these results, we wondered, why did the choroid not thin under blue light? And we thought there's 2 potential reasons for this. One is simply due to longitudinal chromatic aberration. So blue light is refracted more by the eye, and it focuses in front of longer wavelengths, and therefore the eye doesn't need to accommodate as much. So maybe that's why we didn't see choroidal thinning with blue light. increase retinal dopamine and lead to an increase in choroidal thickness. So we conducted a third experiment specifically to test the idea of longitudinal chromatic aberration. So we brought our participants back to this room, and we measured the stimulus response function dynamically and objectively using the Grand-Seiko open field autorefractor under violet, narrowband violet light, blue, green, and red, as well as broadband. So we were also interested in violet light because it seems to be an emerging treatment for myopia that is thought to act on OPM4, which is neuropsin. So we thought, well, we kind of expanded all of our experiments to include violet light now. But for this talk, I'm going to focus on the blue, red, and broadband light and show you what the responses look like for those. This has been demonstrated for decades, actually. Some of the early experiments in accommodation looked at the effects of longitudinal chromatic aberration. So as expected, for a 5 diopter demand, if we look at the dynamic accommodative response, over time, we measured for 30 seconds when they were attempting to accommodate to a 5 diopter demand. And so you can see that indeed for the blue illumination of the room, there was much less accommodative response than for red and for narrowband. So we can see the accommodative response here for blue was significantly reduced compared to broadband and red light. So it leads us to think that there may be less accommodative response, less tension on the posterior eye, and therefore less thinning of the choroid. So I'm leaning toward this biomechanical theory of accommodation playing a role, and I was really moved by a video from some supplemental material that was put out by Kaufman. So this video you can find in IOVS. Let me just play it. It's using ultrasound to image we see the cornea here, ciliary body, ciliary muscle, zonular fibers, the tension zonules, and the posterior eye. And with accommodation, which we can see here, notice how the tension zonules pull on the posterior portion of the eye. And you can see that entire thing being shifted forward. So as we're accommodating all day, as children are accommodating on their mirror work, this is what's happening in their eye. And I think it's putting quite a bit of tension and force on the posterior eye that could certainly lead to this choroidal thinning and ultimately a cue for axial elongation. So with that, how do we finally understand the role of light in mirror work? Because this is something that has been debated for centuries. Is mirror work related to myopia? And I do think that we're getting closer to being able to answer these questions as technology is advancing. So we are using in our lab and in many other labs wearable sensors that can track human behavior objectively and continuously, such as the wrist-worn ActiWatch is a light sensor that also captures the spectral components of light. We're using rangefinders mounted to spectacles that allow us to track mirror work behaviors in children, not just how much mirror work are they doing, but how close is it, are they taking viewing breaks, and those types of metrics. And hopefully look a little bit closer to answering these questions about the role of light and the interaction with mirror work and myopia etiology. So with that, I'd like to thank you for your time, and these are my lab members that have helped collect all this data.
Okay, are there any questions for Lisa?
You need to put the mic on the computer back on.
Any questions? Yes, Amsterdam.
I just want to know, will her slides be available? Sorry. Lisa, thank you very much. It was very informative. Can you hear me? Okay. I just want to know, thank you very much for a very informative presentation. Will you make your slides available to us, or is it unpublished material that we can't send to us yet?
It's kind of half unpublished, but I'm actually happy to share it. So I can send the PDF to Josh, and Josh is free to share with the attendees there.
Okay, I will do that. Any other questions? Yes, Bruce.
Hi, Lisa. This is Wei Zhong from China. Hi. Very interesting talk. In one of your experiments, you were trying to investigate the influence of different wavelength on choroidal thickness, where you test the blue, red, and white light. Yeah. My question is, have you already adjusted the retinal illuminance for these different colors?
I think there may be some differences in retinal luminance, but we do our best to match the power distribution. So we do try to normalize that across the wavelengths. Okay. And we have details of that coming out in our paper that shows the melanistic and cone sensitivities for each light and power associated powers.
Okay, good to know.
Any more questions? Yes.
Thank you, Lisa, for a great presentation. I really enjoyed it. I just have a clarity-seeking question. I'm not sure if I understood you well. In your experiment one, you mentioned that the adults will come in the morning and then watch for 30 minutes and then go home and then come back in the evening. Not sure if I understood you well. And my question is, how did you make sure that you control other factors, that when they get home, they don't continue with more near work, so that your results are reliable? Thank you very much.
Thank you. That's an excellent point. We know that the choroid is very dynamic and responds within minutes to so many different stimuli. So one thing we do for all of our studies that I didn't really talk about was we start with 10-minute distant viewing and control broadband lighting conditions. So we feel that it helps to standardize the conditions that we're measuring, and it seems to help the results be more consistent as well.
Okay. Any last questions for Lisa? Okay, there don't seem to be any questions anymore, Lisa. Thank you very much.
Thanks, John.
Okay, goodbye.
Tanya, she's good.
No, I can go on, Tanya.
while we get ready for Joss to get sorted, we're going to be looking at the Zulu eye next. And then followed by that, Larry will be talking to us.
Okay. So my talk was originally intended for this morning to connect with all the South Africa talks. So I'm obviously not from South Africa. So maybe it's best that I'm a little bit apart from the people that are really from South Africa. So my talk will be on the development of a Zulu eye, and I will develop the reason why, but actually that was already done very well by a young lady this morning, why it's actually necessary to have representation in all the eye models that we use. So first of all, here are my disclosures, nothing related to my talk. I will not repeat that from my other talks, but these are the two. So as was mentioned already a number of times, there's a lot of biometric variation out there. If you just look at all these eyes here, they're all emmetropic, but they're all emmetropic in a different way. This is from a recent paper that I published last May. And there I literally have the quote, there are as many ways for an eye to be emmetropic as there are emmetropic eyes. This is based on a study of 2,000 eyes from Iran. And I was looking at couples of eyes. I was just comparing eyes to see whether they could be distinguished using a biometer. And there were only 3 pairs out of these 2,000 that were indistinguishable within the measurement margins of the device. So pretty much any eye is unique and needs to be treated as such. Now, if you look at different populations, there are also differences. So when we make eye models in general, eye models, well, who are we modeling? Originally, people that developed eye models are people living in Europe. And basically, the eye model was this guy, right? If you're lucky, maybe this guy, but that already forgot half of the European population. So that came only later. And even then, that's Europe. That's not the whole world. So there are a lot of people out there, and we're not serving them. So we need dedicated eye models, and the case was made very well this morning. So let's make one. Now the problem is that we don't always have the right parameters to do that. So what do we need for an eye model? Well, let's make a recipe, simple recipe. You need a measure for corneal curvature, preferably bilateral, anterior and posterior. You need a corneal thickness, that's often available. Anterior chamber depth, not so much of a problem either. Lens thickness, starting to get a bit tricky already. Lens curvature, that's kind of a deal breaker. We rarely have that value. Axial length, that's a very common one. And then refractive index to taste. Pretty much anyone making eye models has their own value. So it doesn't really matter as long as you know which one it is. And you know, overall, these values are pretty close to each other. So that doesn't matter as much as you might think. Just to illustrate, kind of a fun anecdote, if you change the index of the cornea, the corneal power will not change as much because an index increase will increase the anterior corneal power, but at the same time, it will decrease the posterior corneal power by almost as much. So it's not as tricky as you might think. Now, like I said, we have a couple of rare ingredients, and this is where a lot of data sets out there make it difficult to develop eye models. So we need to find a workaround, and that's what I try to present today. So this is the normal way. If you do corneal modeling, this is the normal way. You have anterior cornea, anterior and posterior corneal radii of curvature. Sorry for the abbreviations. So we have this value here, we have that value. This is the refractive index of the cornea. So this is just the standard corneal power anterior. This is standard power posterior. This should not be a secret. And then if you have this value and that value, you can get the total power just by the thick lens equation. This should all be very clear. Now, often we only have the anterior radius of curvature. And then it becomes a little bit more tricky. The first one, the anterior corneal power, no problem. But then we need to take a little detour. We need to take a detour because we can estimate the total corneal power with a keratometric index. Now, often when you use IOL calculation formulas, that value tends to be 1.3375. That's a very common value that you'll see everywhere. Unfortunately, that value is too high. The proper value is probably more like 1.329 somewhere. This is the value that I used, which is comparable to that of Doubleman. It comes straight from the pentagram, comparing anterior and posterior curvatures. That's the value that worked best for the data set that I had at hand. So now I have a anterior power, I have a total power. So how do I get the posterior power or the posterior radius of curvature? We just rewrite this one to get that one. It's just a bit of basic rewriting of the formula. So cornea is set. The lens is a bit more difficult because here we can use the Bennett equation, which looks like this. It looks very intimidating, but all the bits and pieces can be measured quite easily. The only tricky thing is you need to have the lens thickness. That's a bit device dependent. Not every device, every biometer gives you that value, but it's very important. So that's the Bennett equation from 1988. And then there's the Royston equation from 1989 that just basically builds on this one. And if you have these two and you use these values here, where instead of refractive error, you use the refractive error at the corneal vertex. So you just move it to the cornea using this equation, then basically you can calculate the lens power very easily. This can easily be done in Excel. You don't even need to write a computer program for it. So we have a method to build a model. Now the next step is we need data. We need clinical data. So data can come from anywhere. In this case, we got the data. Vanya had arranged it for me. That there would be some data from Zulu eyes that were collected a little while before. There are 192 bright eyes of quite young people. They're pretty much ametropic, and the sex balance is pretty much the same. It was measured in the city of Durban and the suburbs of Durban. So of Zulu people, I really hope I didn't make any mistakes. I hope these are Zulu people. That's at least what Google Images said. And they're the biggest population installed here in South Africa. So they should cover a pretty large deal of the population already. So some European reference data. I had to use the data that was available to me. Much less European data, only 32 right eyes. Gender balance was there. About 5 years older, but that shouldn't make that much of a difference in young eyes, and they were also ametropic. So there was only one issue with both data sets, and that was that the data was for uncycled bleached eyes. That's a bit of a problem, so there might be a little bit of accommodation, making the refractive error a little bit more myopic. I had to use a bit of a dirty trick there. I had in another data set I had found that at the age of 20, the difference between cycloplegic and non-cycloplegic refractive error is about 0.4 diopter. So I simply added that. It's a bit quick and dirty. I would prefer not to do that, but okay. This is between individual eyes, there can be a bit more differences than that. So with all that, I can finally make a Zulu eye model. So what does that look like? Like this. Not very pretty like this, but we can make it a bit more visual. So if you make it more visual, you compare, okay, they look almost the same. And that's, that's to be expected. But the details are quite different. If you look here at the axial length side, the Zulu eyes tend to be a little bit shorter than the European eyes. That's one thing. But also you can see here the anterior cornea are exactly on 0 in both cases. And you see here that the cornea of the Zulu tend to be a little bit thinner. That's true for much of Africa, that they tend to have thinner corneas than Europeans. Also, the anterior chamber that tends to be a little bit shallower as well than Europe. A bit deeper. Sorry, a bit deeper than the Europeans here. And there's also something with the powers, but we can't see that on this slide. For that, I have to go to the next slide. I have to look at numbers, and there you see that indeed the corneal thickness is different by about 0.05 millimeters, so 50 microns difference, which is quite a bit. But also the anterior chamber depth, as I said, a bit deeper in the Zulu, the crystalline lens thickness a bit thinner. But the big thing here is the difference in total corneal power and lens power. You see, it's not significant using a Bonferroni correction. It's not significant that the Zulu eyes are shorter. They're shorter by about a quarter of a diopter, quarter of millimeter, sorry, which would correspond to a corneal power difference of about 0.83. But if the axial length is shorter, then actually that should have been a positive difference, right? So that's not what we're seeing. It's actually a negative difference. And to compensate for that, the lens power is a lot higher. So the balance between the Zulu cornea and lens is different from that in Europeans. As I would call them, the Zulu tend to be a bit more lens heavy, while the Europeans tend to be a little bit more cornea heavy. So there's quite a difference. Another way to illustrate that is this thing. This is something that I'm working on. It's not published yet. These are what I call shape factors of the eye. So here on the horizontal axis, we have the scale factor. The scale factor is just essentially how does the eye scale while still being ametropic, while in the vertical axis, we got the refractive balance component. So here the lens is more important, and here the cornea is more important. So if you look at that diagram and you plot all the eyes, the Zulu eyes in black and the Europeans in red, you see that there is quite a bit of difference. These tend to be more lens heavy, while the Europeans tend to be more cornea heavy. So you see there is again a big difference. Now, why is this important? Well, as was being said before, this is important for things like IOL calculations, for example. So they would need a different A constant for IOL calculations. Also refractive surgery, that might be a different aspect to it. And any other kind of maybe myopia treatment might also work differently in these eyes compared to Europeans. So it's important to study these things and to keep it in mind, at least when you are trying new kind of clinical studies. So as I said, fundamental differences between those two populations, they must be considered. And this method is actually quite simple. I already tried it on different populations. I tried it on some Chinese data that I had available and some Indian data that I had available. And there too, some differences were seen. So whatever I said here also applies to different populations from around the world. So thank you very much. Any questions?
A short question. Yeah. Maybe you have already finish on that. In your last slide, you mentioned, yeah, this modeling strategy is going to already applicable to other operations. Any conclusions?
Not yet. I'm still collecting more and more population from around the world to see, because yeah, if you just have 2 or 3, it's a bit little to get conclusions, but I'm trying to collect as much from the literature as I can. But as you can see, the amount of data that I need is actually quite limited.
Okay, and for the comparisons like this, how can you exclude the influence of different instruments? Difference of instruments.
Difference of instruments, overall, it's not that much. I mean, the differences that we were seeing are definitely going to be a lot more than anything that you might have because of measuring using ultrasound or optical systems. That was actually a difference here between the 2 populations because the Zulu population was measured with ultrasound. However, these things are calibrated against each other, right? So it can't be that you have a 0.26 difference measure with ultrasound versus optical. So if we were talking about 0.05 or something like that, millimeter in action length, you might have a point, but in this case, the differences are still too much for that. Yeah. Any other questions? Yes.
Yeah. Okay.
Thank you for your interesting talk. I was wondering about the lens of the composition of your eye model. How many surfaces is made of? Is like a Ostrin eye model, or how it is the structure of the model?
At this moment, the current form is it's a 2-surface model, so anterior and posterior with a fixed index. That is a limit. I completely agree that that's a limit. It's possible that the Zulu will have a different index, but with the devices that we have available right now, this is the best we can do.
Okay, sorry. And the last one. So, the refractive, yeah, the refractive index, the homogeneous refractive index that you are taking into account is some kind of free parameter, or is something that is measured also? Because it's a mean refractive index, right?
Normally, I would take that as a free parameter, yes. But in this case, I didn't have anything to do that. So what I assumed in this case was that there was a fixed value here, this fixed index, but I had an offset in the radii of curvature. So just to make all the elements meet. So that's another way of doing it. Even if you would not do anything with the images, the conclusions that I gave would still be valid. So Bennett's equation will still be valid. It does not require any of that.
Okay.
So the conclusions remain valid.
Do not depend on that.
No. No.
Thank you.
Most of the instruments assume the refractive index of
Yes.
the optical elements, so it's nothing included.
Yes, that is a very good point. They assume an index and they don't mention it. That's the worst bit. They assume something, and if you ask the engineers, the company, they will not tell you.
Where it's different for chevron camera and it's different for coherence tomography.
Yes. Exactly that. So there is one surface of the lens, luckily, that does not suffer from that, and that is the anterior surface.
But also the wavelength is different, yeah? The wavelength is different.
Yes, and sometimes they may even think about gradient index and not tell you about it. Yeah, that's really annoying.
Is it similar to the less simplification is actually for refractive index of the cornea, and with the lens, it's a bigger problem.
But like I said, the index of the cornea is not as critical. That of the lens is, but the cornea no. So Was there a question?
Oh, okay. Now, actually, one already been asked because the crystalline of the foster is so how did you work it out on that? But then I want to check on the refractive index of how did they come with this? It's based on the 1.3294. All this time we've been using 133.
That's actually my value. That value that you saw just now, that's my value. So how did I come to that? Basically, what I did was the pentagon gives you an anterior curvature and a posterior curvature. So from that, using a using the known index of 1.376, I calculated the total power. And then I derived the curvature index that I needed to get that power from the anterior radius of curvature of the node. You get it? No, I didn't do ray tracing. This is just standard Gaussian optics. Just thick lens equation to calculate the total power, and then trying to match the total power using just the anterior radius of curvature. And for that, I needed that particular value. And that corresponded also with what I could find from the literature. Yeah. Okay. Thank you very much. Oh, sorry.
Just the last time. Thank you, just sorry, just a quick one. Can you shed a bit more light on your sampling method and to what extent we can generalize the Zulu model that you come up with? I think it's a really interesting study that you have conducted.
I cannot really tell you much about the sampling because it was existing data. So it was provided by, I don't fully know the name of
Percy Mashika.
Percy Mashika. So he provided it through Tanya to me. So I also had to make some selection because some data was not complete. So any sampling aspects probably were lost through that selection system because I needed complete data, for example, for each and every one of these individuals. Right. So if for some reason data was missing, I couldn't really use that particular eye. Yeah. Okay. Thank you. And then we come to the main event here. It's Larry Thibos on Zernike polynomials.
Thank you very much, Josh. Well, welcome to the Applegate Thibos course on wavefront error, part 2. Professor Applegate gave a marvelous introduction to the concept of wavefront error. I don't have much to add to correct him in principle, but I hope to fill in some of the blanks where he kind of glossed over a few computational details, and I'm going to try to fill those in for you. It might help to know that the level of the presentation is what I would expect a beginning graduate student to be able to comprehend and learn, but it's not the kind of information that's restricted to graduate students. As I say in the last paragraph of this abstract, I think that a basic understanding of Zernike analysis by clinicians, scientists, and educators will provide an opportunity to gain insight into the effects of ocular aberrations. There's a lot of emphasis on functional consequences on image quality, visual performance, and the underlying cause of the eye's optical flaws. So that's where we're going. And I can appreciate that this is a topic that not everyone is totally familiar with. So I'm going to try to ease into it in a way that will please everyone. On its principle that learning the concepts and jargon of a new field is a bit like learning how to swim, for which there are two very different approaches. One is you jump into the deep end of the pool, you flail about, hoping desperately to discover a way to return to dry land before you drown. The other way is much more gentle. It's to enter the shallow end of the pool, and you learn basic skills like how to float, how to do the dog paddle before you venture into deep water. So we are going to take the second approach. Now I'm going to throw it. Yes, I'm not going to throw you in the deep end of the pool and hope that you survive. So let's look at the big picture of what the tutorial is about. This is Applegate lovely diagram in which she defined the wavefront error as the difference between the ideal wavefront, that's the green one, and the actual wavefront, that's the yellow one. And that difference is measured. Well, you can put a ruler in there and measure that distance. It's a pretty small distance. They typically are on the order of a wavelength of light, just microns in length. But we're going to try to explain how those wavefront error measurements can be usefully summarized by a mathematical formula. And when we have that mathematical formula, there's lots of amazing things you can do with it computationally, but you got to get the formula first. And that's what Zernike analysis is about. And the components of that analysis are going to be Zernike polynomials. So when I first started putting this tutorial together, I called it Zernike polynomials, a primer, but really it's a bigger topic than that. It's not just the polynomials themselves, it's the whole concept of Zernike analysis of the wavefront error function. So one of the first questions you might have is, how am I ever going to get a ruler inside the eye to measure those little distances? It's all well and good to say, oh, that's the distance, but that's a closed system. You can't get a ruler in there to actually measure it. And we're going to talk more about that. Applegate and I will talk about that a bit more tomorrow, and I'll briefly touch on it in a minute, but I can give you a clue, and that is we're not going to take the light from the outside to the inside. We're going to do backwards. We're going to put a light source on the retina and let the light come out. So we're going to measure those distances in object space, not the image space. But we'll make the argument that they're pretty close to it being the same thing. So that'll ease your mind that it is actually physically possible to measure those tiny little distances. Okay, so here's the lesson plan. I'm going to start simple. So I'm going to do it with an analogy from a different kind of analysis, one called Fourier analysis, in honor of Mr. Fourier himself, from 1700 or so. It's been around a long time, 400 years worth, as opposed to Zernike analysis has been around for about a century. That's quite a bit of time too. Zernike analysis has been widely used in optics fields other than optometry and ophthalmology. It's taken quite a long time for it to percolate into the visual science community, but it's been around for a long time. So I'm going to start with that simple analysis of analogy with Fourier analysis, and the reason is because the Zernike analysis is much like Fourier analysis. It just builds upon it in one extra stage of complexity. So if you can get the guts of the idea of Fourier analysis, you're on your way to understanding what Zernike analysis is about. Then I'm going to show you some pictures of what these so-called Zernike polynomials are about, arranged in something I call a periodic table. There'll be a mathematical description of those. In other words, a formula that describes those polynomials. And then how you determine the coefficients. Those are the weighting coefficients. And then about half of the lecture will be about practical uses of these Zernike coefficients and the Zernike formulas, using both physical and geometrical optics. So we'll start with something familiar. How do we start with the problem of specifying the power of an astigmatic eye? We've already heard a bit about that this morning. Here's my take on the idea. First, I've got this other theory that words are really very important to scientists because the words we use determines the way we think. So let's get our words right. Power versus vergence. So one of the mantras or one of the recurring lessons I give to all my students in the past. I've been retired for like 12 or 13 years, so it's been a while. But the idea was that lenses have power. and they have the power to change the vergence of light. So power and vergence are kind of similar things, but they're not the same. Vergence is a property of the light. Power is a property of the lens. But they can actually be numerically equal. For if you have a lens that is impaled by a plane wave of light and has zero vergence, then when it comes out is a wavefront that has the vergence equal to the power of the lens. It just inherits that power. So we can talk about the power of spherocylindrical lenses, and bless them, our South African friends are actually experts in this topic. As thanks largely to Bill Harris, who resurrected the topic from the doldrums of ignorance back about the late 1980s, a long time ago. We really started a mathematical analysis that helped clarify a lot about what astigmatic lenses were about. At that time, I never met Bill, and I didn't know anything about his work, so I had the pleasure of discovering it myself in a very different sort of way. Here's the way I looked at it, and that is, yes, Professor Applegate, as I said, I give him credit for teaching me almost everything I know about, I say almost everything I know about visual optometric optics. And one of the things he told me was that wavefront power varies sinusoidally with meridian. That's power profile, it's called. Power varies sinusoidally with meridian. And as I just said, if you had a plane wave coming in, what would come out would be a wavefront that has vergence that varies sinusoidally with meridian. Now, I come from a discipline that uses Fourier analysis every day. I'm an engineer by training, and I look at that curve right there, and I immediately think of Fourier analysis. Because Fourier analysis would tell me that this lovely sine wave can be defined by just three numbers. And those three numbers are the mean. In other words, the sum of all these positive values and then plus all the negative values, they all cancel one out, and that's the mean value. And that's the kind of power profile you would get from an ordinary spherical lens of a certain number of diopters, in this case, 2 diopter lens. In addition, you have this sinusoidal variation, and the difference between the peak and the mean is the amplitude of this sine wave. And that's what we refer to as the amount of astigmatism. Now, I speak differently, but I don't say this is the amplitude of a cylinder. I'm talking about the amplitude of astigmatism. So it's a different word because it's a little bit different idea. So traditionally in optometry, you think of spheres and cylinders. I don't think in terms of spheres and cylinders. I think in terms of sphere, mean power or mean vergence, and the amplitude of the sinusoidal variation. So that's two numbers. The third one is what meridian is responsible for. It occurs at the peak of the sinusoidal variance. Okay, and that's related to the axis of your astigmatism. So three numbers come out. If you think about them in polar coordinates, they are the mean, the amount of astigmatism, that's J, and alpha is this angle for which the peak curve occurs. And the reason for choosing the letter J was because that's the kind of wave front that you would get a sinusoidal variation about 0 is the thing you would get if you had a Jackson cross cylinder lens. And the clinicians told me about Jackson cross cylinder lenses. They were a kind of a specialty lens, he said. You used it at the very end of the refraction just to see if you got things right. But to me, they were a fundamental lens. You should make your phoropter out of Jackson cross cylinder lenses. It'd be a lot easier to learn how they work. Tom Rash from Ohio State University has actually done that. Anyway, in polar coordinates, those are the three numbers. And we would call these Fourier coefficients M, J, and alpha. But now you can also, I should have talked about this coordinate system, of course, center of the pupil, X, Y, theta is the meridian, a radial distance away from the center is our parameter. So we can talk about it in radial coordinates, or we can put it into Cartesian coordinates. And so if you do that polar to Cartesian conversion, you can basically turn a vector into, again, the main a component in the x direction and a component in the y direction. And those became the three components of a power vector. And Alan told you about power vectors just a little bit earlier this morning. And they've been quite popular because it's a nice way to describe astigmatism or a spheral cylindrical lens. Right? Okay, so as a summary statement, then what I'm trying to do here is describe the shape of a curve. This curve is to be drawn in the plane of the board here of the slide, and it's a one-dimensional curve. I mean, there's only, it's a one-dimensional curve. It takes two-dimensional graph to show it, and it's easily described by just three numbers. What's going to happen with Zernike analysis is we're going to reuse that meridional axis. That's one of the free parameters, but the other axis will be the radial distance. See, the nice thing about standard optometric optics of spherical cylindrical lenses is that you would get exactly the same profile no matter where you look in that pupil plane or on the lens. It's the same everywhere. And that's why the R parameter, the radial parameter, doesn't matter. It's got left out. It's been hanging around waiting for a long time for people to realize, maybe the radial distance matters. And it does when you have what's called the higher order aberrations. Then that radial parameter starts to matter. So we have that will be the elaboration of Fourier analysis to turn it into Zernike analysis. So let's learn Fourier analysis is a process of systematic decomposition of the shape of a continuous curve. Now I gave you a very simple one, but you could have really complicated one-dimensional curves and break it down systematically into a sum of sine waves. And the sine waves will each have a different harmonic. First harmonic is one cycle and 360 degrees. Astigmatism, it's two cycles. And that's why, you go to 180, nobody ever describes the cylinder lens as axis that I know, 230. It's because when you get to 180, you start over again. It's the same axis now. And then the third harmonic, fourth harmonic, you can have as many harmonics as necessary. And you can call those sinusoidal modes, if you like. And they are going to be summarized by a mathematical equation, which is called a Fourier series or a Fourier expansion. And you'll have a function of an equation that will tell you exactly how this one-dimensional curve can be reconstructed by adding up a weighted sum of sinusoids. And that's what Fourier analysis does. Zernike analysis is going to be similar, but we're not going to talk about the shape of a curve, but the shape of a surface, because the wavefront error function is a surface in 2 dimensions. It's a 2-dimensional surface. These weights are an efficient code that can be used to recreate the curve. That's good. You can just tell somebody the 3 harmonic or those 3 numbers, and they can reproduce the whole curve for you with that power profile. It's a nice way to report the data. And nicely, individual modes correspond to specific types of optical aberrations, such as defocus and astigmatism. Now, it might be possible to move into the domain of wavefront error functions using Fourier analysis, but it turns out to be not a good choice. And the reason is the Fourier analysis, when generalized to 2-dimensional data sets, are what you would call a grating. These are sinusoids. And this is the best picture for my talk. It's a corrugated sinusoid. It goes up and down, up and down, up and down like that. And you'll be measuring the height as a function of position. And then you have to have a whole bunch of them, all different orientations, you see, to be able to create a description of an arbitrary surface. But the main problem with this, 2 main problems. One is missing corners. You see, pupils tend to be circular, not square. If you had square pupils in your eye, then Fourier analysis would be the ticket. You just go, you never have to learn about Zernike and his polynomials. You would just use 2-dimensional Fourier analysis because it's perfectly set up for square pupils. Not many of us have square pupils. What Zernike did was he developed these functions so they were perfect for circular functions defined over a circle. And that's why they're often called Zernike's circle polynomials, because there are other kinds. There are also Zernike elliptical polynomials, for example, where you have an elliptical base for your surface, which could be used, by the way, if you're looking obliquely into an eye, because when you look at a circle obliquely, it looks like an ellipse. It's foreshortened. So you could use Zernike's elliptical polynomial, but we're not going to go there today. The other problem is that none of these basis functions, these building blocks that we're going to build up our surface with, correspond to individual aberrations. I mean, who ever seen an aberration that makes one of those grating sort of things? I mean, lenses don't do that, you see. So there's no natural correspondence between the basis functions, these building blocks, and the operations that we're familiar with. So they just don't work very well for optics. It's setting the optical imaging capabilities of an optical system. So instead, we're going to use these guys. These are the Zernike polygons, just a few of them, just to show you an example of what they look like. Ray already gave you a bit of a hint. The one at the top is a plane, and depending on how you orient it, it can be tip, it can be tilt, and you really only need two of them. You can build any sort of shape you want by adding one with tip and one with tilt. Yeah, any orientation plane at all. Okay. These are the second order modes that optometrists make their money with. Spherical lens, rotational symmetry, the astigmatic lens, or the astigmatic wavefront. That's the kind of wavefront you would get if you passed a plane wave through a Jackson-Crowe cylinder. And you're just spinning around there for your delight so you can see the shape. A couple others. Here's a so-called third order aberrations. Coma, one trefoil. You see, it's got three peaks. So it goes from peak to trough to peak 3 times as you go around the pupil. And go around just imagine yourself walking on the margin of the pupil at the edge. We go up, down, down, 3 times. Third order. So the basic proposition of Zernike analysis, or the end goal, is to write an equation that looks like this. Wavefront error equals the sum of the product of two things. One of those things is a number. That's a coefficient. That's how much you have of this basis function. The other thing is z, which is one of these shapes. You see? So let's take the familiar example that I have an astigmatic eye. Let's say I don't have any other aberrations in my eye. I just have astigmatism and defocus. So I've got a spherocylindrical refractive error. What would I need to describe that wavefront error? Well, it would be a certain amount of that and a certain amount of this at a particular orientation. I have to freeze that picture to get the axis just right. And see, those are my 3 numbers, like the mean, the amplitude, that's the amount of astigmatism, and the axis. To do the same thing in Cartesian coordinates is we will choose 2 of these kind of at right angles. One will be oriented so that it's the peaks kind of go north, south, up and down. And the other one, they'll be off horizontal, like this, 45 degrees like that. So again, we have just 3 modes. We're going to add them together, give them different weights, and we now have a formula for that wavefront error function. If I happen to have other aberrations as well, I just have to have some more of these things, and I'm going to add them all up. But these are the basic building blocks. So when Ray and I started mucking about with this technology, gosh, more than 20 years ago now, Ray was going to put together a book called Customized Corneal Ablation, Early Days of Refractive Surgery. And they had a goal of correcting not just the ordinary spherocylindrical refractive errors, but all of the higher order aberrations as well. So we had to educate the ophthalmologists how to think about aberrations when there's more than just these 3 surfaces, more than just those spherocylindrical ones. We might have some of that, some of that, some of that, some of that, some of that. And we're going to have to add them all up. So we needed a picture because, I mean, who wants to look at an equation and figure out what its shape it is? A picture is worth 1,000 equations. So we put together this little table showing in a very systematic way how these Zernike polynomials are going to look. And they have basically two independent dimensions. One is the meridional frequency. That's the same kind of frequency we had with Fourier analysis. One cycle or 0 cycles. That means this one has rotational symmetry. It doesn't cycle at all as you go around the pupil. First harmonic, that's this one. It will cycle once as you go around the circle. Second harmonic, that's our lovely Jackson cross-cylinder formula here, J1 or J0, I mean. It cycles twice and so on. So that's the meridional frequency. So it's just like Fourier analysis. Now, what's different about that is we've got a second independent parameter now, which has to do with the radius. And what's called the radial order. First order, second order, third order, fourth order, fifth order, and so on. And that table goes down, down, down as far as it needs to go. And it's going to be called the order because you will see in a minute why they're called polynomials. They haven't shown a polynomial yet. It's all been trigonometric functions, but I'm almost there. Here we are. Oops. Here's another way to see the shape, but a little bit different, but it's useful in its own way. It's kind of like heat maps, no color. This is black and white. It's a little bit better in that it gives you a top-down look at the pupil. And so you can see that this one, for example, bright means it's high, dark means it's low. This is the peak, that's the trough. And you see how the peak cycles once and twice to get back like this one. This one goes around once, twice, 3 times. And this one, the peak is on the horizon, on the 0 meridian. Whereas the corresponding one over here, I better do this one, it'll be easier for you. That's horizontal. This one's at the 45-degree axis. So that's the Jackson cross cylinder oriented with the axes vertical and horizontal. And this is the Jackson cross cylinder when they're actually at 45, 135. Okay? These are associated with the sine function, the trigonometric sine function. These are cosine because the cosine of 0 is maximum. The cosine wave is maximum at the angle of 0. So that's why that's the cosine. Over here, the cosine is, or the sine wave is at 0 at the axis 0. So these on the left-hand side, they're all going to be sine waves, and on the right-hand side, they're all going to be cosine waves, and the order will determine the polynomial. And I finally get a chance to show you the equations. I'll just show you one, get that basic idea. The anatomy of a typical polynomial. I'm going to do it in polar coordinates first, and then Cartesian. I have to do it twice because for thinking, polar is by far the best way to think. It's just like in the optometry, you want to think in terms of power and axis. You don't want to think in terms of, it's easier with polar. So what do we got? We've got a weighting coefficient. That's the Zernike coefficient, tells you how much of this shape we're going to have. And back up here. What do I do? Oh, there we are. We have a normalization factor. That's a mathematical nicety. It helps. It's useful. It will make the variance of this equal to 1. And then we have the polynomial. 3 rho cubed minus 2 rho. Two things to say about that. One is the order of a polynomial, if you remember your math education, is the power, the highest power that exists in that polynomial. The highest power you see here, that's a 1, that's a 3. Highest number is 3. So it's a third order polynomial. And that's what we call this, a third order Zernike function. Now, the other thing to say about it is normalized rho is the normalized radius. What that means is we're going to take all of our radial dimensions and divide by the actual radius of the pupil. So the maximum value of rho is going to be 1. And it's a convenient thing to do. You don't have to do it, but Zernike did, and he did it because it's going to make a whole lot easier to do the arithmetic. In fact, you only have to know these polynomials. You only have to evaluate them once. They'll always be the same no matter how big your pupil is. So it's a convenience factor. And then we have what is basically a Fourier term. So when I showed you the Fourier analysis example, I didn't have any of that. I just had a Fourier coefficient and a sine wave or a cosine wave. Now we've got this polynomial, and that will tell us how this wavefront error is going to vary with radial distance from the pupil center. Okay. There's a whole bunch of them. Now you get a sense that they all look the same basic structure. They got a normalizing constant, a polynomial, and either a sine or a cosine. And every one of them has got a name associated with it. See, they got a nice one-to-one correspondence with real optical aberrations. So, you know, this is a no-brainer. These are really useful polynomials. Of course, we're going to use them. In fact, now it's an international standard for reporting optical aberrations of eyes. You report Zernike coefficients if you want to get published. Now, having said how wonderful that is to see it all in polar coordinates, in fact, when you come to use them, polar coordinates are horrible to work with. It's much better to convert polar to Cartesian coordinates. And when you do that conversion, you get a lovely formula like this instead of that. Well, you know, I don't know about your brain, but I can sort of picture this sine wave going around. It's got to go like a cubic function of radius. When I look at this equation, I have no idea what that shape is. It just doesn't connect mentally. I see these things. That's the first time I looked at Zernike polynomials, I was seeing this kind of stuff. I had no idea what the picture was. So I just had to graph it. I had to write computer programs that would plot it out. Okay. So, bunch of rationale. Why are we using these anyway? They're a complete set of functions, by the way. I got these basic building blocks. I didn't really advertise it. I really should have done that. You know, I just got to advertise this. This is a nice idea. This is a periodic table of basic functions. Now, you studied chemistry, right? You had to do that if you want to graduate. And you learned about how the basic structure of an atom is determined by, you know, how many protons it is and how many neutrons and all that stuff. And when you lay it all out to say that all the basic atoms, like, or elements like hydrogen and oxygen and carbon and all those, you lay them out in this table, they call it a periodic table of the elements. Well, those are chemical elements, and they're very fundamental. If you want to make a molecule, you got to use the stuff that's in that table. And the way they're laid on the table tells you a lot about the nature of that atom and what kind of physical properties it's going to have, what it's going to be used for, all that stuff. Same thing for these. It's a very basic fundamental layout of all the different kinds of polynomials. And they're going to give you a way to conceptually think about how each of these contributes to the retinal image. Okay, so other things, they're orthogonal. That's a kind of a nice computational feature, and they're all normalized to unit variance. It makes it easy to sum up. If you got a whole bunch of Zernike polynomials, you're going to add them all up to make a wavefront error function. You want to know what's the contribution of each one. You just look at the coefficient, because the coefficient will tell you the variance in each one. Okay, quick note about how do we get the data. We're going to talk about this tomorrow, but the basic idea is that you put a spot of light on someplace on the retina that you're interested in, let the light come out, and then you image the light with an array of little lenses, and they'll make that light want to get bent in a prismatic sort of way, and you can measure the deviations from the standard, and you've got the wavefront arrow. So I'm going to get to that. Why you skip through that? Because I want to get to practical uses for. I tend to get distracted by my own enthusiasm. I don't want to miss out on the applications here. First of all, they're an efficient and unambiguous way to record data. That's why it's a standard. It can be useful statistically too to evaluate the quality of a fit. Big one is to assess the relative strength of the aberration modes by inspecting Zernike spectra, and there's one that you'll like, determining the refractive state of the eye. So I'm talking now about the weighting coefficients, not the polynomials themselves. What good are the coefficients? So let me draw you another analogy. When you're thinking about completely different context, think about the contrast sensitivity function of the eye, of vision. Yeah. What are you thinking about? You're thinking about, I'm going to look at a grating, a sinusoidal grating, and I'm going to figure out how much contrast you have to have in that grating so that you can either detect it or resolve it, something like that. Right? And the sensitivity is like the inverse of the contrast that's just detectable. And then you think, now, how does that vary with the spatial frequency of the grating? Yeah. And you get this thing in your mind, you get this little curve goes, it peaks at around 6 cycles per degree, and it falls off about 50 cycles per degree. You're thinking in the frequency domain when you do that. Nobody says anything about space. This is frequency is the independent axis, and in contrast on the other axis. That's the contrast sensitivity function. You're already thinking in the frequency domain instead of the spatial domain. You transferred your query, the question in your mind from one domain to another because it's a better way to think. And Zernike's analysis is very much like that. But our frequency domain here is kind of a two-dimensional domain. It's not just a one-dimensional domain of Fourier analysis where you talk about radial frequency. You have to divide it up into different orders as well. So this is the other domain, the other dimension of the frequency domain. And so when you plot out data like that, because you're asking yourself, in a population of normal, well-focused eyes, where's all the energy going into these wavefront error functions? Are they concentrated on the second order, and the third order, the fourth order? Well, most of them are, most of the error is in the second order. Standard spherocylindrical refractive error. They're much bigger than the third order or the fourth order. And within that second order, what's the biggest value? It's in the middle, defocused. Yeah. The astigmatisms are smaller. Third order, they're about the same, a little bit smaller here. Fourth order, one really stands up, spherical aberration. So you're starting to think in this two-dimensional frequency domain about how the different components of a wavefront error function are being distributed. And you can learn things, for example, like how much does the wavefront variance vary with order? Varies a lot. It's a very rapid decline. So if you sum across meridian on those data, you get a curve like this. It falls off as a straight line on a logarithmic axis. That means it's falling off exponentially. The amount of variance contributed by higher order aberrations falls off very fast. Second order is the biggest. Okay, and the last use of the Zernike coefficients that probably received the most attention in practical use has been, let's estimate refractive error. No, not just spherical refractive error, but the full spherocylindrical refractive error. And there's a simple little way to convert your Zernike coefficient into the main sphere J0, J45, the three components of a polar vector. They're directly proportional to the Zernike coefficients. So it's a pretty easy shot to get an estimate of refractive error from Zernike coefficients if you want to put them into the dioptric, you see. However, you can't necessarily expect that that's going to be the one true answer in an eye that has higher order aberrations. If your eye only had second order aberrations, then bingo, you're kind of done. If it only has second order aberrations, you only need 3 Zernike coefficients, you know. that one, and that one, the 3 second order coefficients. Huh? And you'd be done. It'd be perfect. But if you have other aberrations in there as well, what can you say? What you say is that these 3 numbers, these second order coefficients, they represent the best fit in the mean least squares sense. You know, whenever you do any kind of curve fitting, you're always using a least squares algorithm, which is to say you sum the difference between what you got and your model, add up all the squares and try to minimize the sum of squared errors. And that's how you find the best model. It's the least squares method. It's used universally in all branches of math and applied science. And that's what Zernike analysis does. It tries to find the least squares fit. So the least squares fit is not equivalent. And there's our other, I gotta have another advertisement. I object to the whole use of the term spherical equivalent when talking about a just ordinary sort of refractive error. And the reason is because equivalent means equal. And a sphere is not equal to a spherocylindrical lens because it doesn't have any astigmatism. It's not equal. So you shouldn't say mean spherical or it's spherical mean spherical equivalent because that's not equivalent. You should say mean sphere. And then you realize, of course, it's not equivalent. That's why I didn't use the word equivalent. It's just my best fit. It's my best approximation. And so it is here. The best focus or best fitting sphere would only need one Zernike coefficient. It would need that one, but it is not equivalent to necessarily to the far point. It doesn't tell you the far point of the eye. Because by other criteria, you can get a different answer. And the different answer depends on, well, what's your criteria? If you looked at the paraxial rays, they could be focusing down there. You say, that's the far point. Or you look at the marginal rays. You say, no, that's the far point. You can do a Zernike analysis and say, that's the far point. They're all approximations. It all depends on what your criterion is. And then you say, ray, what's the best one for vision? That's what I want. Fair enough. Of course, there's lots of ways to characterize vision as well, so you're not necessarily out of hot water, but you get the impression that they're not necessarily a unique answer. And what Zernike analysis is trying to just do for you is give you the best fitting spherical, spherocylindrically fit to a true wavefront aberration function. Okay. So I don't know, I forgot to turn my watch on. I don't know how much time I'm going to have left here, but I got to tell you about the practical uses of the Zernike expansion. That's where the real power here is, and using both geometrical and physical optics. So first, physical optics. Ray showed you lots of great pictures of Bohr light chart and things like that. See, how'd you calculate those, Ray? You know, and say, well, I used physical optics, didn't I? Is that right, Ray? Hey, I use physical optics. So a real quick tour of what physical optics can do for you if you know the wavefront error function. The wavefront error function is used as a fundamental component of something that's a little more complicated. It's called the pupil function. The pupil function, P, depends on the XY coordinates in the pupil, and has 2 components. One is a transmission component. Unless you're interested in cataracts or something, you just let that be 1, and you move on to this thing, the exponential of I, K is a constant, times W x1. W, this is the wavefront error function we've been trying to get a hold of. A formula, a Zernike formula is going to be put in there. And it's got this funny thing, I, which happens to be the square root of -1. So people that are used to dealing with this kind of stuff, oh, that's a complex exponential. And that makes things a little bit more complicated mathematically, but we can deal with it. Take the pupil function and look at this diagram, which is just a cartoon. It's a schematic view of what you can do if you have a pupil function. There's our pupil function, whatever it is. There are 2 ways to characterize, 2 general ways to characterize the imaging quality of an optical system. One is the optical transfer function. How does the transmission of the system vary with spatial frequency? It's a lot like, conceptually, it's a lot like a contrast sensitivity function. How does the contrast on the retina, how does it depend on spatial frequency? And that can be computed from the pupil function by a mathematical operation called autocorrelation. And the other convenient and fundamental way is the so-called point spread function. And that's where we show lots of examples of how the image of a point of light gets spread out. That's the point spread function. Here's an example of the airy disk. That's your airy disk in profile. And that can be computed from this one using something called the Fourier transform. Huh? And there's another route you can do, by the way. You can go this way too. You can go from here and get an amplitude spread function using the inverse Fourier transform. Find the magnitude, that's complex value, you find the magnitude, and you get this one as well. So this is where the power lies. If you want to, say, calculate the image for some grading, you use it one or the other, depending on whether you want to solve the problem in the frequency domain or in the spatial domain. And they both are derived from that pupil function, which itself is derived from the wavefront error function. I want to spend a little bit of time on geometrical optics, because I really think we've undervalued the role of geometrical optics in all of this wavefront aberration stuff that's been going on for the last 20 years. So let's look a little more detail at what Ray told us before, which is you have a reference sphere and you have a wavefront. There's a difference between the two. And he said that is a difference between those two, that little distance. That's the wavefront error. That's what we're describing with our Zernike equations. Huh? So think about now the fact that, as Ray said, rays of light are always perpendicular to the wavefront. These are both geometrical concepts, and they are always perpendicular to each other. Because the ray is telling you the direction of propagation. So for a little patch of light, Ray said that's like a plane wave right there. And that plane wave is propagating in this direction. So think now logically that if these two curves are different like this, there's a gap in between them, that means that the slope of this one must be different from the slope of that one. Right? They have to have different slopes because there's a gap between them. And they have continuous curves coming out from the pupil. Right? They have different slopes. Okay, one of those lines is going to come down. That's our reference, and that's the ideal place to have the light rays end up. But it's not going to end up there, is it? Because the slope over here is different. In this case, it's a bit steeper, and consequently, the ray of light is going to go down like this. It's going to hit the retina down there. And that's bad news for our imaging. You don't want the light from the same point source to end up, some of it, it's going to end up there, some of it's going to end up there, some there. It's be all spread out, you see? So this difference between the reference rays direction and the actual rays dimension is reference and the actual ray. That's that little angle delta. That's called the ray aberration. And the ray aberration in general is different for every point in the pupil. But that's okay, because we have a formula that tells us what the wavefront error is every place in the pupil. That's what Zernike analysis does for you. And all you have to do is take that formula and calculate the slope. And we do that with calculus, take the derivative. And usually you do it in Cartesian coordinates. You take the horizontal derivative and the vertical derivative, and together it will tell you the direction of the ray. So delta actually has two components. It's got a horizontal and a vertical component. Okay, so all of that's happening back here in the pupil domain. But what you really want to know now is what's happening in the image domain. Where is point P? Where is that landing? You know, if you were in a different branch of optics besides eyeballs, you might say, oh, I'll just measure that distance, 2 millimeters or something, and I'm done. But that doesn't work with eyes because the eye is a closed system and you can't get a ruler in there anyway. You have no idea where that ray is going to hit in terms of linear distances. but you can tell their visual angle, and that's what we do. Where I say that's the point in my peripheral field. It's the only real angle. Where is it on my retina? You wouldn't say it's 1 millimeter or something. No, you say it's 20 degrees out. It's a visual angle. And so this point here, right here, has a visual angle associated with it. That's angle phi. If you project it out into outer space here, into object space, you say, oh, that object point, that image point is out there, 15 degrees out or something. So this is the visual angle associated with that point. And all this, the deviation of P from R is called the transverse aberration. So the two terms, one's the ray aberration, that's in the pupil plane. Transverse aberrations are in the image plane. And you say, no, I'd like to link the two together. Oh, I hope it works. I hope there's a link between the two and all the big buildup. And guess what? They're almost equal. I say almost because there's a small approximation you have to make when analyzing this geometry. But phi and delta are almost equal. Okay, and most times we just say they're equal. In fact, instruments are built that way. They're built that way. So that if you measure the wavefront slope, you know where the rays can hit in the retina. Yeah. And so if you take lots and lots and lots of points in the pupil, calculate all those slopes, find out where all those points are, and guess what you got? Something called a spot diagram. Optical engineers have been doing this stuff forever. We're just learning how to do this visual optics. Sure, it's slow. So that's the spot diagram, and here's a way of depicting it. When these heat maps, it's a simple zero astigmatic wavefront. And what these little arrows show you is where each ray is deviated. This ray, at that point, this is the ray error. This ray is trying to go that way. It's supposed to be going to the middle, but it doesn't go that way. They're all going in different directions. And if you follow that logic we've just been in, you can say that each of those arrows corresponds to a dot over here. Say that dot is where this ray is going to end up in the visual field, on the retina and in the visual field. So this is image location is an angular dimension. And all those little black dots correspond to all those little arrows that represent the slopes of the wavefront, where the rays are going. Those are the ray errors. These are the transverse aberration errors. And then you say, well, it's nice seeing all those spots. Where did you get the red circle? We've got a formula, and we can evaluate that formula with the finest interpolation you might want. We may have 100 points measured empirically to collect data to make a wavefront aberration, a wavefront error function. But once you've got the function, you can evaluate it every micron in the pupil if you wanted to. You get 1 million estimates of the spots. And that's what they did here. If I blew that up, there's 1 million little red spots there that are just being interpolated between by making use of the Zernike polynomial. Right? So that Zernike expand, that's one of the great uses of the Zernike expansion of a wavefront error function. You got yourself a formula you can use to interpolate empirical data. Now, I don't know how much longer I can go on like this, but I got a great demonstration for you here. It's about skew rays. Skew rays scare the devil out of most optometry students. That's why when we talk about astigmatism, what do? We talk about the principal meridians, because they're the easy ones. Rays that come in on a principal meridian stay in the plane of incidence, and in the plane of the diagram. Skew rays don't do that. They're very badly behaved. So this little diagram that I have to admit I use many times in optometry school teaching kids this stuff, it's a lie. It's a lie. I have to admit it. But I wouldn't admit to my students that it's dishonest or something. But honestly, it's a lie. And the reason is because this ray almost always does not intersect this axis. So if you're in the habit of saying, oh, what's the versions of that ray? Oh, I know, I'll just say 1 over that distance. Surely that's the versions of that ray. No, because they don't intersect. Almost none of the rays in your eye will ever intersect that optical axis. If you've got astigmatism, and only astigmatism, the only ones that will intersect the optical axis are the rays in the principal meridian. And that's just a small subset of all the rays. And if you get any other higher order aberration like coma or truffle or anything, you won't have any rays. Well, none of them will intersect that axis. So it's a complete fabrication. But we do it because it's simple and it gets the initial point home. And then you have to abandon that. You have to say, oh, that's not right. And it reminds me of this wonderful, Penrose, he's a really bright guy from the days gone by. He had this illusion, which is very much like that illusion right there. You look at that triangle and you kind of fall around. It's impossible. You couldn't build one of those. It's impossible. It's called the impossible triangle. But guess what? There's some really clever guys in Australia named Brian McCain and Ahmed Abbas in Perth, Australia, who built one. They built one. Look right there it is. That's Penrose's impossible triangle. They say, oh, how did they do that? They say, you move your camera over a little bit. Say, oh, I get it. They didn't intersect. That's the optical axis. This is my skew ray. Those that they don't intersect. They don't intersect. But from a certain point of view, they seem to. And that was the little lie. From a certain perspective, they seem to be able to intersect, but they don't. Nevertheless, another theory that I've told you is going to break down because we don't really care if that ray intersects the axis. I didn't use that information at all to tell you about how you make a spot diagram. So in the end, you can get out things that you're very familiar with. Alan showed us a power cross earlier. Optometrists love power crosses. I think that's the one thing I didn't learn from Ray. I learned it from a graduate student. He was an optometry student. He was all the time drawing power cross. So what the heck is that? Now, I didn't know what he was talking about. These are Virgin's crosses. And you can make a Virgin's cross. At every point in the pupil, you can find the principal meridians of that cirro-cylindrical wavefront, local. So they're very localized at that point. And so here's our favorite astigmatism example. At every point, I can find the two principal meridians and make the length of the power cross equal to the amount of virgins in that principal meridian. You completely populate that wavefront error function, and you can do the kind of linear algebra that ladies like our heroine, Tanya Edmonds, would just love to get her teeth into. That's just like the power, what do you call dioptric power matrix? Yeah, go the dioptric power matrix, and they use this self-volume all the time. It represents the second derivative. So when we finally get to the final thing that optometrists want to talk about, which is dioptric power, you go past the first stage of taking the slope, which is the first derivative, to get to the second derivative of the wavefront. Because that tells you about the curvature of the wavefront. And it's curvature of the wavefront that is the vergence of the wavefront. What is it? Curvature of the surface is the vergence of the wavefront. And so we can just take the second derivative, and you can even make a little dioptric power matrix like that, and do some magical things, which I'm probably going to run out of energy to tell you about. But here's a better example, coma. Let's look at the power matrix for coma. It's different everywhere. I mean, these are the ray errors. These are the vergence errors. And this one's got, they're all the different axes, they're different lengths, they're different everywhere. Well, that's the way vergence errors really are. And an eye that's a bit of coma. It's pretty easy to get coma. I've got coma. You've got coma. All you have to do is decenter the lens from the cornea a little bit. You'll get coma because they both have spherical aberration. They decenter one spherically aberrated lens from another, you get coma. And so we all have coma. And so our power crosses, our vergence crosses are going to be like that all over the place. So if you really are in love with dioptric way of describing wavefront on the optical errors of the eye. This is the ticket home for you. Yeah. Yeah. Okay. Well, I'm sure I ran out of time. Oh, okay. Gaussian curvature. Gaussian, great topic. So this is for the advanced students here, or for Gaussian curvature. It's really cool stuff. It's calculated as the product of the surface's principal curvatures. Huh? We just talked about the principal curvatures. At every point, you find the principal curvatures of the wavefront. If you multiply those two together, you get something they call Gaussian curvature. And mathematicians, love this sort of thing. They do differential geometry. They talk about Gaussian curvatures all the time. But what's really good for us is that the Gaussian curvature tells you how much light is going to be, what the illuminance of the retina is going to be for every little patch of wavefront in the pupil plane. And the reason is because that Gaussian curvature tells you the size of them. Like, think of the blur circle or the blur ellipse. In general, at every point in the pupil plane, the wavefront is locally cylindrical. That means it's going to produce a blur ellipse, not a blur circle, if there's a symbolism. It'll be a blur ellipse. And this principal curvature, the product of principal curvatures, tells you the area of that ellipse. Well, it's possible for the principal curvature to end up all the way down to 0. Yeah. We were talking about the divergence error matrix, not the divergence itself, but the divergence error matrix. And when that principal curvature drops to 0, the product is 0. That means that all of the light that went through a little patch of the pupil ends up in an area of a spot with 0 area. Now that is really high density. That's a certain amount of light per 0 unit of area. That's like infinite illuminance of the retina. Yeah. Now it doesn't actually get that like that because that's a geometrical optics approximation. And as we told us, physical optics says the light gets diffracted, spread out a little bit. Nevertheless, you can tell that there's going to be something really exciting happening on the retinal image if you ever get a Gaussian curvature of 0. And that interesting thing is called acoustic. And acoustics are well known in the many fields of optics. You go and have a drink tonight, and you have a glass of wine, and somebody set up spotlight, and you'll see this beautiful pattern on the tablecloth. And the number right along is acoustic. And the one that's universally known is you go outside, and this morning we saw Venus up in the eastern sky. Just for instance, before we went on our ride, I don't know if you looked up, but before we went on our ride this morning, Venus is very, very bright. And some of the bright stars are going to give you a starburst as well. When you look at that star and say, it's not a single point of light. It's got bursts of light going out, little caustics. And you can predict what part of the pupil produced the caustic. Now, that might actually have clinical utility, because I understand from people that have intraocular lens replacements and other kinds of refractive surgery, sometimes their starbursts are even bigger than normal. They're super big. And you might wonder, well, I wonder if I can get rid of those starbursts. Yeah, maybe there may be a therapeutic value here, because you can find all the places in the pupil where the Gaussian curvature has gone to 0. Like all those little spots in the pupil where the curvature has gone to 0, that's what produces the caustic. This little sequence there, that produced a caustic. It's just one example of how you can diagnose where in the pupil caustics are being generated. Okay, well, that's just about the end. Imaging, Ray's already giving demonstrations of imaging. And you see what he skipped. He said, well, we're just going to take the Zernike coefficients to produce an image. Well, you have to go through all the steps we just talked about the past outline to get to the point where you can produce a calculated image for any object. And what do you need? You need the spot diagram if you're doing geometrical optics, or the point spread function if you're using physical optics. You take that little fella and you do a mathematical operation called convolution. You convolve that spread function with the object, and you've computed the image. And that's that example. That's the object. This is an example of a point spread function, convolve the two, and you get the blurry image. That's the way you do the calculation. But it all goes back to quantifying that wavefront error function, and that's why it's so fundamental. And that's what everybody should know, because if you're interested in images and you're going to rely on some machine to calculate that for you, I believe you should know the principles by which that calculation is done. Never know. Maybe they made a mistake. You don't want to trust your life on it or your patient's condition. You got to know the principles involved anyway, even if you don't do it yourself. Okay, I'm sure I exhausted you as well as me. I should stop. Thank you for your patience.
Yeah, I'll translate to Larry. He asked me to translate.
My ears, they just don't work anymore. They're horrible. So.
Questions?
If you got a question, ask him and he'll tell me. Whisper in my ear. I'm good at lip reading. Lip reading really helps a lot. There's a lot of sound information in people's lips.
Yeah.
Visual information.
So are there some questions?
Anybody got any questions?
Thank you for your very interesting talk, Dr. Larry. What is the case in which the error between making backwards or forward the ray tracing between in the eye that you mentioned about the difference in those angles? What is the case in which this error is minimum?
So he's asking why in wavefront sensing is there a little error in the use of light coming from the back of the eye?
Oh, yeah. Well, if you look at detail at the actual path, if you look at the actual path of the ray coming in, and then look at the path of the ray that's going to go out, they're similar, but they're not exactly the same. Okay. And so, I mean, that's sort of my answer. I mean, people talk about the reversibility of optics and stuff, but it's the two ray paths are not exactly the same. And so, because like all the outgoing rays come from one point on the retina in an objective aberrometer. You put a laser beam in there, and all those rays are going to come from that one spot. But when going in, they start with one spot, but they don't end up at the same place. You see, so that they're conceptually similar and they are kind of reverses of each other, but not exactly the same.
They're close enough.
And it is worse for skew ray than for meridional ray? The approximation? Is the approximation worse for skew rays than for meridional rays?
So he's wondering if meridional rays are the same or affected in the same manner as skew rays. On skew rays, yeah, for the reversibility. What you were just explaining, leaving one dot on the
right. Yeah, you skew rays as well on the reverse path. You know, these rays coming out of the eye from a point source on the retina. Even if you like to think, you like to think of a myopic and icer example because the far point is right there. I can touch it. So you're imagining that all these rays are going to come out from a point and end up in a point. And they're going to cross that line of sight that connects the two. But if there is any kind of aberration other than that defocus, those rays are going to be skewed. They're going to go up in some different direction.
In fact, that's what we capitalize on to measure.
Yeah. Here we are over here.
Oh, we missed something. I'm so sorry. This one?
Thank you.
Hi, Doc. I have a question, but I'm not sure if it's really related to what you said. But like, I would like to know if, because some patients, when you test them, sometimes they don't have like any pathologies. You refer them, they refer them back. They say give your best BA. And when you do the test, there's no lens appreciation, meaning that they can't take any lens, it doesn't make any difference. So my question is it possible that higher order aberrations, they can cause like amblyopia? in such cases, and also like knowledge appreciation.
I'll just answer that for you.
Go ahead.
Okay. And the answer is yes. So what you're, so.
What's the question? I'll answer what the question was.
Okay, okay. I'll repeat. So she was saying, in some patients, right, you start putting lenses in and they can't tell the difference. And she was wondering if that's due to the skew rates. Yeah. So I was going to answer that for her. All right. So you have to think about what the patient is doing during a refraction. You've asked them a question. You didn't ask them if they're skew rays or anything else. You just asked them a question. So if the image is so bad because of the skew rays, right, and you put a lens in, as far as they're concerned, it made no difference, right? And that's why we have to know the wavefront error so we can correct it. So not just say, you never correct sphere and cylinder when you're correcting someone. That's a lie. What you're doing is the patient has all these aberrations and they're picking the best sphere and cylinder according to what they like. Right? And that's what we do. We have the power of changing three things.
Yeah.
Sphere, cylinder, and axis. All right. And the rays go where they go. And if those rays can't be corrected by sphere, cylinder, and axis, it didn't get better. Okay. Yeah.
That's right. And mathematically, what we're doing is using the mean sum of squares algorithm to find that best fit. But what the patient does is what looks the best to them, whatever is going on in their head. And it depends on the object they're looking at. You might get the best fit if they're looking at the letters on an eye chart, and then you start seeing photographs on your iPhone. I said, well, don't look very good. Well, it's a different object. Might need different prescription.
Yeah, and if you measure refractive error with sphere and cylinder as a function of pupil size, you get different answers. Right. So it's strange.
Is there another question? No. I know. Should we go now? That's the question. No.
Thank you.
Thank you, Naomi. Right, so that concludes today's conferencing component. There is just less than an hour for those of you that want to go for a self-drive or a nap or a walk, whatever you want to do. Okay, so we'll have dinner at 8:30 in the dining room.
Was at 7:30.
18, 6. Tomorrow morning's program starts with a hot air balloon ride for those of you that booked. And at this point, it's confirmed. Okay, they're watching the weather. So there is still a small chance that it might get postponed, but at this point, it's confirmed. And they've asked us to meet in reception at 5:15. So not quite 4 o'clock like they told us. 5:15. Yeah.
I meet at 5:15.
You could sleep in one more.
Okay. You'll have seen from this morning, please, wind chill factor, please put on your jackets. You can always strip it off. I did notice that the hot air balloon people this morning came back after us, which means we may need to push the program out again tomorrow. But as soon as we get back, we'll try and get the message through to everybody, if that is the case. Any questions on logistics?
Maybe somebody wants to go for this hot air balloon because I asked for 3 And the information was that if I will find the next three, I can go. So even two. If somebody is undecided, so maybe you want?
My wife wants to go.
Yeah.
So it's one. Only my wife.
One. So we have one. So we have five. Somebody.
Okay, one more person. All right, thank you, everybody. See you later.